Hello everyone. Today, in this video, it's going to be a shorter format. We're mainly going to go over the formation and reactions of enolate anions, and we're going to go over Aldol reactions. We will talk a little bit about Claisen condensations, but we will not get too deep into Claisen condensations. It's mainly going to be these two topics today. So let's get started into how enolate anions can be formed. So for example, if we have a acetaldehyde, something like so. Let's just give a general example instead. For example, if we have something like this, and if we were to introduce a base to this compound, it's going to deprotonate, and it's going to form our enolate anion. Put that negative charge on the oxygen, but we can also put down its resonance structure, which looks like so. And this resonance structure is what we're mainly going to be looking at today. So this is how a enolate is formed. This is the synthesis of an enolate. And let's go over the reactions of these enolates. They are pretty simple. So either one, we have our enolate here, with a negative charge, and it's going to be a classic SN2 reaction. So if we have something that looks like this, this will undergo an SN2 reaction into something that looks like this, which is something we've seen before. So that's pretty simple, and they can also react with stuff like ketones. So this is this is acro addition, and it's going to end up looking like this. So this is the basic mechanism of how enolates will react. So either in a SN2 reaction or carbonyl addition, this is nucleophilic acro addition. So let's move on to how some particularities about enolate ions. So enolate ions can react both at the oxygen or at the carbon. So let's put drawing enolate ion here. And the negative charge on that carbon. This enolate can react either at this oxygen or at this carbon. So if we have a compound here, this can react either at the oxygen, which will form a vinyl ether, and this will be from the resonance. This is the same as this. It just results from the resonance structure, which is similar here of the enolate. Or it can react at the carbon bearing the negative charge, which will look like this as a product. So for the purposes of this video, we're going to mainly focus on the reactions at the carbon, and you can steer the reaction towards the reaction at the oxygen. However, primarily you'll see the reactions at the carbon due to counter ions. So counter ions such as lithium or sodium are going to be much more closely associated with the oxygen compared to the carbon there. So this is going to make generally the reaction favor a reaction at the carbon bearing the alpha carbon bearing the negative charge. So this will always be at the alpha carbon here. So how this works is that these counter ions, these ions that you will probably get from the formation of an enolate itself, you can't just have an OH, so it either has to be lithium OH or sodium. So these ions are resulted from the formation of an enolate, and these ions will be much more closely associated with this oxygen. It's because they're going to hover near the oxygen much more than the carbon, and that these ions, counter ions, will block approaching electrophiles. So like this electrophilic carbon here, they will block electrophilic carbons to some degree, and they're going to favor a reaction at the alpha carbon instead. All right, let's move on. So, let's go over Aldol reactions. So, Aldol reactions are nucleophilic additions of an enolate anion from a aldehyde or ketone, adding to the carbonyl group of another molecule of the same or different compound. So we're going to first go over self-Aldol reactions, which are going to be reactions of a compound reacting it with the self. And later we can look a little bit at cross-Aldol reactions, which is two different compounds reacting. So Aldol reactions can be catalyzed either by acid or base. However, I recommend going through the base catalyzed reactions first because they're much easier to see the mechanism, see through it. And once you're good with the base, I recommend going through the acid then. However, Aldol reactions can be catalyzed by either. So we will go through both mechanisms in this video. So let's go through an example of an Aldol reaction. So if we acetaldehyde, if I have acetaldehyde, it's just a very simple thing. And I'm going to write these in different colors so it's easier to see which parts added to which. So I'm going to draw this in blue. So these two are both acetaldehyde, ethanol, and they're going to undergo an Aldol reaction in the presence catalyzed by an NaOH, a base, and the resulting product will be something that looks like this. OH attached to COH. So you can see which two parts added together. So the pink part came from the first compound, and the blue part came from the second compound. So you're going to see there's going to be a 1, 2, 3 relationship from the carbonyl carbon. So this is going to be the third carbon, which gets attached to the carbonyl group. So, or you can look through a alpha beta relationship. So this is the alpha carbon, which is the first carbon adjacent to the carbonyl group, and this will be the beta carbon that will be attached to the second compound through Aldol reactions. So this is an example of a self-Aldol reaction because both of these are the same compounds. So let's go over another reaction. If we have acetone, let me write this in a different color so it's easier to see. If we have acetone, we can have 2 acetone. Both of these are acetone, and this can undergo an Aldol reaction in the presence of a base. It doesn't matter what base. It can be barium, sodium, lithium, anything. So we can use barium if you want, just any base. And it's going to undergo an Aldol reaction catalyzed by that base. So the product will look like this. And notice how the carbon is connected from the third carbon from the third carbon from the carbonyl group. So this is alpha and beta, 1, 2, 3, like so. So in this case, this carbon will act as an electrophile, and this carbon will act as a nucleophile. So let's go over the mechanism of this reaction. As I said before, most an Aldol reaction and enolate reactions will usually follow these steps outlined here. So let's go over the reactions. So the first step is deprotonation. So as before, the base is going to come in and deprotonate a alpha hydrogen, and this is the alpha carbon. It's going to give our resonance stabilized enolate anion there. So the position of this equilibrium actually strongly favors the left. So this is not actually thermodynamically favorable, but we're going to go over how we can make this more favorable through specifically LDA, make this a kinetic reaction. But for the purposes of this video, we're just going to look at the reactions. So after our enolate anion is formed, it either undergoes an SN2 reaction, so the nucleophilic is going to go for the electrophilic and is going to attach each other, or it goes through acro addition, where the nucleophilic carbon is going to go for the the electrophilic carbon is going to go for the nucleophilic carbon and attach itself like that. So let's go over our first reaction in the context of an Aldol reaction. So our first reaction was H3COH. So let's draw it this way. H2H. So in base is going to come in and deprotonate this compound, which is slipping my acetaldehyde. And after this base has deprotonated this acetaldehyde, it's going to form our resonance stabilized enolate. Notice how the equilibrium lies strongly on the left here. And this is going to create our resonance stabilized enolate. It's going to form water. And our enolate anion, which will look like this. And its resonance structure, which looks like this. And then that's the first step. The second step is going to be the formation of a new bond between a nucleophile and electrophile. So in the context of our first reaction, this would be our second bit of acetaldehyde. Plus our enolate anion. So this is going to react where this is going to come in and attack that carbon. Like so. And it's going to create a new bond between the nucleophilic carbon and the electrophilic carbon. And it's going to form a tetrahedral carbonyl addition compound. I accidentally made a mistake, and these are in opposite colors from the reaction up here, but it's the same gist. So notice how this alpha carbon here is deprotonated and goes for another carbon, and therefore making this the beta carbon once the reaction has completed. So this intermediate can then be quenched and protonated in the third step to give us our Aldol product, and it will regenerate our new base catalyst. So if we can just do water, and this is going to pronate our product, and it will be something that looks like this. Or whatever. I think we use sodium up here, yeah. So, and our base product. So the base is now consumed and it acts as a catalyst in our Aldol reaction. This is technically the third step here. It's a separate step. All right. Let's move on to the mechanism of acid catalyzed Aldol reactions. And usually what you want to remember is that base catalyzed will usually enhance the nucleophile, and acid catalyzed will usually enhance the electrophile. Don't worry too much about the acid catalyzed Aldol reaction. We're going to go over the mechanism of it, but I recommend studying the base catalyzed version, as it is a lot more simple than the acid catalyzed version, easier to see at least. So the first step in the acid catalyzed formation, acid catalyzed Aldol reaction, is going to be keto enol tautomerism. Catalyzed by an acid. So this is actually we went through this in an earlier video. This is acid catalyzed equilibration of a keto enol product. So first of all, we're going to catalyze the equalization of our keto and enol forms. And second, we're going to protonate. So it's going to pronate the oxygen. And give us our oxonium ion. And then this is in the next step, we're going to form a new bond between a nucleophile and electrophilic carbon. So this product is going to undergo attack from the NO of one molecule on the pronated carbonyl group of another molecule, and it's going to form a new carbon-carbon bond. So this is the NO form of our starting product material. And this is going to form a new carbon-carbon bond, like so. I should have put this in different colors. I'll show which came from which. So as you can see, this forms our a product intermediate. So the second blue part comes from here, and the pink part comes from this first molecule there. And this, in the next step, is going to deprotonate through proton transfer. So the acid is just going to come in. Acid we had earlier is just going to come in and take away a proton. And this is going to give us our Aldol product. Here. And it's going to give us our acid back. So those are the two mechanisms of acid or base catalyzed Aldol reactions. And we're going to do some examples. So, for example, let's do some examples. Yeah. Let's do some review for simple examples. So, let's call that A. Let's call this B. Let's call this C. And let's call this D. So, which one of these compounds are going to be the most acidic? So go ahead and try that. So it's going to be compound C, because in order for our compound to be most acidic, the enolate formation can be stabilized by either oxygens on the alpha carbon from the alpha carbon. So it can be stabilized by that oxygen or that oxygen. And if we had an alpha carbon here, it can only be stabilized by one. If we had an alpha carbon there, it can only be stabilized by one. And if we had an alpha carbon here, it can only be stabilized by one. So C is going to be the most acidic carbonyl compound. So let's go on to a simpler question. If we had 4 compounds, let's call that A. Let's call that this B. C and D. So out of these 4 compounds, which one is the most and least acidic? Rank these compounds from least to most acidic. So go ahead and give that a try. So the least acidic compound here is going to be C. The second least acidic is going to be B. And the third least acidic, well, the second most acidic is going to be A, and the most acidic is going to be D. So D is most acidic because it's a carboxylic acid, so that makes it automatically more acidic than the rest of these. So what we're interested in is why A is more acidic than C, and B is just in between A and C. So A is more acidic because the alpha carbon here in the center can be stabilized by either oxygens on either sides. However, and so can C. However, in C's case, because of these 2 ether groups on the side, it's going to block a little bit block the delocalization of the alpha carbon charge, and it's going to cause C to be less acidic than A. So if we have electron stabilizing groups, such as these ethers, they're going to interfere with the delocalization of the charge on the alpha carbon, and they're going to result in a less acidic compound than if we didn't have electron stabilizing groups such as the ether. The contents of this chapter is very important to understand the basics from before. So the basic reactions from the previous videos should be understood. So let's go through an example for that. If we were to react this compound in this order of reactions, what would be our major product from this reaction? So go ahead and give that a try. Okay, so all of these reactions are reactions from previous videos. So the first step is going to be hydrolysis. This hydrolysis is going to hydrolyze this ether here, and it's going to give us a carboxylic acid group. So 1 and 2 are each going to be hydrolysis. So 2 just serves to protonate. So the end result from step 1 will look like this. And step 2 will protonate that oxygen and give us a carboxylic acid here. And step 3 is going to just be decarboxylation of the carboxylic acid, and it's going to give us our end product, which will look like this. So this is the end product from that reaction that we just did. This reaction right here. This is the end product. So let's go through decarboxylation a bit more. If we had multiple carboxylic acid groups, and we were to decarboxylate using heat, what would be the end product from this reaction? So go ahead and try this reaction. Pause the video or whatever. So the end product from this reaction is going to be this. So if we look at our starting product, we have 2, 3. So how do we choose which one to decarboxylate? So the answer is we want a 1, 2, 3 relationship from the carbonyl group. So from 1, 2, 3, or the other way, 1, 2, 3, we want to get rid of either of these. However, if we look at the carboxyl group at the end there, we can see it's 1, 2, 3, 4, 1, 2, 3, 4. So we want to get rid of either of these, and this would not be a good target for decarboxylation. Instead of 1, 2, 3, you can also look at alpha beta carbons. So we want to decarboxylate the beta carbons there. So this is going to be our end product. Let's go through one last example. So if you can do this example, I say you're pretty well set on the mechanisms that we need to know for this topic. So first, so what is going to be the product of this reaction here? So go ahead and give this a try. All right, let's go through this. So the first step is going to, this ether is going to be generating a negative charge on the alpha carbon here. So the first step will generate a negative charge. The second step is going to be the formation of a new bond. So an SN2 reaction is going to add on to 1, 2, 3, 4. So it's going to add on to the carbon there with the negative charge. So 1, 2, 3, 4 to form this product with the this thing we just added dangling down. And step 3 is going to generate another negative charge on this alpha carbon. And this is going to actually cause a ring formation due to the generation of that negative charge. So this will actually cause the formation of a 5-membered ring due to the negative charge, and the chlorine will be gone. So this is the end result of step 3. Step 4 is going to be hydrolysis. So these ethers are both going to be hydrolyzed into OH groups. And these are going to be, well, technically it should look like this. Step 5 is going to be protonating these oxygens. And step 6 is going to be decarboxylation. So you can take off either of those carboxylic acid, and it's going to give us the end result, which will look like that. So that reaction earlier, this will be the end result. All right, let's move on. So Aldol products will undergo dehydration very rapidly. Well, yeah, for most Aldol reactions, most of the Aldol product is going to dehydrate, and a very little product is going to be present at equilibrium. So let's go through the dehydration of our Aldol product. So if we have CH3, CH, CH2, CH, and this is our Aldol product. It's actually the product from earlier, we formed earlier. So this would be the alpha, and this would be the beta carbon. So either in warm water or in acid or base, this can be this will undergo dehydration, and it's going to give us a alpha beta unsaturated aldehyde or a ketone. So this is going to form this product, dehydrated product here. And this here is mostly what you will see as a product. So whenever you see something like this, you have to think about the Aldol product that correspond to this dehydrated, unsaturated, dehydrated aldehyde. So you can see that it's going to be an OH and the H from here, and it's going to lose the water. So we're not gonna go over the exact steps of dehydration, just know that most aldol product at equilibrium will dehydrate or reverse into the starting materials. So next, we're going to go over crossed aldol reactions. So what we've been doing now is self-aldol reactions where the same molecule reacts, but now let's go over crossed aldol reactions. So, for example, this. Let's draw this in a different color. This is formaldehyde. It's the simplest aldehyde. So this is a crossed aldol reaction. It's two different molecules, and it's going to form a product under acid. Base or acid, but in this case is base. It's going to form this product here. So it's similar to the self-aldol reactions, except in a cross-aldol reaction, one molecule provides the enolate ion and the different molecule provides the carbonyl group. And of course, this molecule can actually undergo self-aldol reactions. So this could be a side reaction that occurs to form another different product from this desired product. Formaldehyde will just deprotonate. It lacks a alpha carbon, so it cannot actually undergo self-aldol reactions. So there are some reactants that cannot form an enolate ions, especially ones that do not have alpha hydrogens or alpha carbons. So formaldehyde does not have an alpha carbon at all. An example that does have an alpha carbon but no alpha hydrogens is benzaldehyde. So this benzaldehyde, and this cannot undergo self-aldol reactions either. But these can be trivial. It's just a way to eliminate at least one extra reaction that you don't want. So another thing is that nitro groups can be introduced as a substitute for nucleophiles. So we can instead have something like this. And this is going to create an anion which can be stabilized by charge delocalization. So this is also a way this will create this anion, which will behave very similarly to a nucleophile used in an aldol reaction. So this can actually basically just be an nucleophile instead of a enolate as a nucleophile in the aldol reaction. This is stabilized by delocalization, charge delocalization, So, but I'm not going to draw the resonance structure. You guys can imagine it. So, one very important thing is that the reduction of the nitro group, if we were to form an aldol product with this anion, the reduction of the nitro group in the product formed is a very convenient way to synthesize beta amino alcohols. So it's very useful in drug synthetic chemistry. There can also be intramolecular aldol reactions. So intramolecular aldol reactions are very useful for the formation of 5 or 6 membered rings. So if we have, for example, this compound, it's 1, 2, 3, 4, 5, 6, 7, 8 carbons. So this is 27-octodione. So this can undergo self-aldol reactions to form a ring. So it can either undergo a aldol reaction at the first alpha carbon, or an aldol reaction at alpha carbon 3. So 1, 2, 3. So either the carbon 2, or carbon 3. So it can undergo reactions at carbon 1 or carbon 3. So if the reaction undergoes at carbon 3, it's going to form a 5-membered ring. So this is going to cause a charge, negative charge on that. It's going to cause a negative charge on carbon 3. This is carbon 1. And this is going to close the ring and form our 5-membered ring product. So basically like that. So this is the end. This is the aldol product, but remember that aldol product will dehydrate into the final form, which is going to look like this. So when you think about aldol product, you always want to think about a dehydration. This can if we look at this from the reaction at, let me move that. At the first alpha carbon, it's going to form a 7-membered ring, but the 7-membered ring formation is strongly not favored compared to our 5-membered ring product here. So whenever you see something like this, intramolecular aldol reaction, most of the time it's going to occur at carbon 3 here and form a 5-membered ring instead of a 7-membered ring. 2, 3, 4, 5, 6, 7, yeah. So a 6-membered ring can also form when in an intramolecular aldol reaction. So it can specifically form in comparison to a 4-membered ring. It will actually always form instead of a 4-membered ring because it's more stable. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So carbon 1 and carbon 3. So one, two, three, four, five, six. 1, 2, 3, 4, 5, 6. Whoops. Should actually look like this. So this is going to undergo a intramolecular autoreaction, and it's going to give us a product that looks like 2, 3, look like this. And this is going to dehydrate and form our final product. All right. We're not actually going to go over Claisen condensation today, because I actually spent longer than expected talking. So that will be the next video. Thank you everyone for watching, and